keep it real with emotion. Marching,
Hello and welcome to the concepts video on other trig functions. So other means like other than sine and cosine like we've already learned, but that's what I'm going to start off with, is saying, okay, so let's say we have this circle, okay, and we divide it up into quadrants, alrighty, and let's say we're here, okay, and we have a radius of r on our circle and an angle of theta. So at this xy point, we move x in the x direction and y up in the y direction, up and down, okay, so we've already defined sine and cosine, right? So we already have that sine of theta is equal to y over r, okay? That was defined for us. We have that cosine theta is equal to x over r. And I gave you a preview on the last video that tangent is equal to y over x, okay? So we know these ones. This counts as other too, because we haven't technically learned that yet. So tangent is equal to y over x. Now we know, formally. And we also have three other ones as well. We have so this is called tangent. I'll just write it out. So tangent is here. We also have one called cosecant, and that would be CSC theta is equal to r over y. So the flip of sine, right? We have a normal secant, not the co kind, but the secant, and that's SEC of theta is equal to r over x. So that's the flip of cosine. And we have cotangent, which is denoted by COT, theta is equal to x over y. So that's the flip of tangent, okay? So we can make some relations here and say that, so sine theta is equal to y over r, which is equal to saying 1 over r over y, right? Which is 1 over cosecant theta. So we can also say, just in a less confusing manner, that cosecant theta is equal to 1 over sine theta. So we're most commonly going to see this kind of relation here. We can also say similarly that secant theta is equal to 1 over cosine, okay, because it's just the flip of it, the reciprocal. And finally, we can say cotangent theta is equal to 1 over tangent theta, okay? So these are three important identities here. And again, identity means no matter what value you plug in for your variable, okay? It's also worthwhile to mention that tangent is kind of a special trig function. Tangent's special because tangent of theta is equal to y over x, which when we look at our triangle that we form here, y over x, that actually tells us the slope of our line, right? Because that's like rise over run. So this is slope of line. It could tell us that, and that could come in handy in some cases. Okay, and it also tells us that tangent theta is equal to, let's say we were to break this up and say y over r. I don't know why I'm sticking an r in there, but just for demonstrative purposes. So we could break it up like that, because you could always cancel out these r's, right? But what I'm doing here is saying that we can actually rewrite this as y over x over r. And you might recognize this as sine theta on the top and cosine theta on the bottom, okay? So here's another important trig identity. Tangent theta is equal to sine theta, which is like your y, over cosine theta, which is like your x, okay? So there's another biggie there. So before we take on this problem here, I'm going to kind of make an important side note here that every trig function somehow can be phrased in terms of sine and cosine. Can and does stem from sine and cosine. Sine and cosine, okay? And that's important because we already know a lot about sine and cosine, right? About certain angles and like 30 degrees, 60 degrees, 45 degrees, things like that, and we can just apply our knowledge in order to figure out characteristics of other trig functions, okay? So keeping that in mind, now let's try to look at and solve this problem. So it says evaluate tangent of 45 degrees and secant of 5 pi over 6. So if we look at tangent, so we have tangent of 45 degrees, we already have that we can rephrase tangent as sine over cosine of that same angle, right? So sine of 45 over cosine of 45. And we can recall that sine of 45 degrees is radical 2 over 2. And cosine is also radical 2 over 2 there at 45 degrees. So that means that our tangent at 45 is simply going to be a 1, okay? And now let's try the secant thing. So secant of 5 pi over 6, we can rephrase secant as 1 over cosine of that same angle. Okay, and we can kind of identify what cosine is. So let's draw a little sketch of our unit circle. So this is 5 pi over 6, so we have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, and 5 pi over 6 is here. So cosine is the x value there, so it'll be negative and kind of a big number. So it goes more in the x direction, in the negative x direction, than it does the y. So that means we're going to need the bigger value, which is radical 3 over 2. Okay, so this is going to be, when we take the reciprocal, negative 2 over radical 3, which we can rationalize and say that's negative 2 radical 3 over 3. Okay? Okay, so now to introduce a term that I've kind of defined informally during a previous video. So identity. What does that mean? An identity is basically an equation that holds true for any values of your variable or variables. Okay? Variable or variables if you have more. Okay, and oftentimes I introduce this because oftentimes we're asked to prove trig identities. So ones involving trig functions, such as sine, cosine, tangent, any of the 6 that we've learned. Okay, and it's kind of like a puzzle. What we do is you can take 2 approaches. There's pick one side, pick more complicated side, like the left side of the equation or the right side, and try to simplify to look like the other side. Simplify, okay? Or we can work from both sides at the same time. Work from both sides at the same time. But then that gets a little bit tricky sometimes because then you can be going in the wrong direction. But anyways, you can work from both sides at the same time. Sometimes it does work for some particular problems. It kind of just depends on the question you're given. Or you can kind of just try pretty much anything that's mathematically legal, that is, or mathematically correct, equivalent. So try anything to obtain an equation where you get something, so I'll just write squiggly, something is equal to that same exact something, okay? And then once you get to a point where the left side is exactly equal to the right side, then you've proved that identity, okay? So let's try an example of this. Okay, so it says to establish the identity, this thing, okay? So the left side definitely looks more complicated than the right side, so we could just start working from the left side. And the thing is, with any kind of identity, there may or may not be different ways of how you can prove it or establish it. So there could be different routes of solving, but sometimes there is only one route. But for this case, there are multiple. But what I'm going to do is actually something, I guess, a little bit kind of creative. What we're going to do is take this 1 plus sine theta on the bottom, and we're going to multiply it on both sides. Okay, so we're going to multiply the left side by 1 plus sine theta, and we're going to multiply the right side by 1 plus sine theta. Okay, so on the left side, those ones cancel out, and we just get cosine squared theta, okay, and then is equal to this thing on the right. But what this turns out to be is 1 minus sine theta plus sine theta minus sine squared theta, right? So these guys cancel out, and we get cosine squared theta is equal to 1 minus sine squared theta, okay? And now what we can do is just add that sine squared on both sides. So you might see where this is going. Okay, and we get back to cosine squared theta plus sine squared theta is equal to 1, which is actually our Pythagorean identity, right? Which we can pretty much almost always take to be true now that we've proved it. But anyways, so we could always formally, to complete this proof, we could say that the left side by the Pythagorean identity is equal to 1. So n1 is equal to 1. So that completes our proof and we are done. Or that completes our establishing the identity. Alrighty, now we have another problem. It says if tangent theta is equal to 2 over 7 and theta is in the third quadrant, find cosine of theta. So for this one, I'm going to draw out a picture. So let's say we have our circle, right? And then our quadrants here, and quadrant 3 is down here. Okay, so tangent theta is somewhere, so theta is somewhere here. Okay, so we have our triangle, let's say, and here's theta. So let me blow up this triangle a little bit. So here's theta. Alrighty, so that's kind of like our reference angle. We could also say theta includes all of that as well, but for our purposes, we only need the reference angle part. Okay, so the thing is that tangent of something is equal to, let's say this is r, this is x, and this is y. So tangent theta is equal to y over x, right? And in our case, tangent theta equals positive 2 over positive 7. But for our case, we see that x should be negative and y should be negative, which makes sense. So we could have had negative 2 over negative 7. And then in that case, the negatives just cancel out and we get positive. So in doing that, I'm saying that, okay, so y should be negative 2. Okay, so this is negative 2, and x should be our negative 7. Okay? So, and we just figured that out by combining our the information we know that theta is in the third quadrant, meaning that x is negative and y is negative. Okay? As well as the information about tangent, and what it means is that it's y over x. Okay? So now we figured out that our triangle hold on, let me actually draw a line. There we go. Okay, so our triangle looks like this. That's negative 7, that's negative 2. We can kind of ignore the signs. And our r is equal to, it should be by the Pythagorean theorem, then it would be the square of the sides, or the square root of the sides. So r is equal to the square root of 2 squared, so that's 4, plus 7 squared, that's 49, so that's equal to the square root of 53. Okay? Square root of 53. So in order to find cosine theta, we just apply our formula that cosine theta is equal to x over r. So adjacent over hypotenuse, this guy. So we get negative 7 over the square root of 53. Okay? And that's pretty much it. You can rationalize it if you want. Negative 7 radical 53 over 53. And that's completely fine as well. Okay, so that concludes our concepts video on other trig functions. I hope that helps, and I'll talk to you in the practice problems video if you watch.